Hi learners, today we shall learn about differentiability, some basic rules of differentiation, and then the relationship between continuity and differentiability, and some examples also.
Suppose f be a real function and c be a point in its domain. Then the limit f of c plus h minus f of c divided by h as h tends to 0 if it exits. If it exits means exits as a finite number. Then this limit is what is called the derivative of f at c. If this limit doesn't exist, we say that the function is not differentiable at that point c. Now what about the derivative of a function? The function defined by f dash x equals limit of f of x plus h minus fx whole divided by h as h tends to 0 if it exits. That is, if this limit exists, then only we can say this function is what is called the derivative of the function f. That is, dy by dx means to differentiate the function y is equal to f of x with respect to x. As a part of algebra of derivatives, we can have derivative of a sum or difference is nothing but the sum or difference of their derivatives, and derivative of a product is nothing but u into derivative of the second plus derivative of the first into second function, that is u dash v, and then u by v the whole dash, that is derivative of a quotient, that is equal to, we can have u dash v minus uv dash by v square, where v not equal to 0. This all formulae theorems we studied in 11th class. If a function f is differentiable at a point, say c, then it is continuous at that point. C. That is, if the function f is differentiable at a point, then automatically it has to be continuous at that point. Then what is the proof of this theorem? So for x not equal to c, we can consider f of x minus f of c is equal to f of x minus f of c divided by x minus c into x minus c. Because x not equal to c. Since x not equal to c, x minus c not equal to 0. So this expression is valid. Now we shall go with the limit of fx minus f of c as x tends to c, that is equal to limit of f of x minus f of c as x tends to c divided by x minus c, and limit of x tends to c then x minus c. Now what happened? This expression, that is limit of fx minus fc divided by x minus c as x tends to c, it is nothing but a f dash c. It is nothing but a derivative of the function at x equal to c. So we can write that is f dash c, and it is given that the function is differentiable at c, therefore f dash c exits as a finite number. So f dash c exits as a finite number into limit of x minus c as x tends to c. You know that is x minus c being a polynomial, then we can substitute directly x equal to c, that is c minus c, because we know that when a function is continuous, we can go with the value of the function in place of a limit value. So instead of finding the limit value here, we can go with the direct value, that is c minus c. But what is c minus c? C minus c is a 0. So the right hand side becomes a 0. Now what about the left hand side? That is limit of fx minus f of c as x tends to c. This is our left hand side, and we can expand it, that is limit of fx as x tends to c is equal to limit of x tends to c f of c. And we know that this is a constant, and the limit of a constant is the same constant only, so we can write. So what the equation we got? That is very interesting equation, that is limit of the function as x tends to c equals value of the function at that point, which implies that f is continuous at x equal to c. F is continuous because value of the function equals the limit of the function as x tends to c. So thus we could prove that whenever a function is differentiable at a point c, it has to be continuous at that point c. Now what about, thus we could prove that whenever a function is differentiable, it implies a continuity. That is true. Then what about the converse of this property? That is, suppose the function is continuous, then can you claim that is it differentiable at that point? Answer is we cannot. Why? Because we know that the function say y is equal to modulus x. In the last class we could see that this function, modulus function, absolute value function, is continuous. We could prove it by taking 0 as a special case, and for real numbers negative and real numbers positive, then we could prove that function is continuous everywhere. Everywhere means at all points in its domain. So y is equal to mod x is continuous. But at the same time we can show that it is not differentiable. In order to say that modulus function is differentiable, it has to be differentiable at every point in its domain. But we are going to prove that modulus function is not differentiable. Modulus function is not differentiable at x equal to 0. Then how to prove it? Recollect that f dash c is equal to limit h tends to 0 f of c plus h minus f of c divided by h. Therefore we have to find f dash 0, that is limit h tends to 0 f of 0 plus h minus f of 0 divided by h. Now you know that modulus function is defined as a multi-branch function, that is negative x if x is less than 0 and positive x if x is greater than or is equal to 0. So therefore here we have to find left hand limit and right hand limit separately. Frankly speaking, we have to find the left hand derivative, that is the left hand limit actually. So that is, we have to find limit h tends to 0 minus f of 0 plus h, f of 0 plus h minus f of 0 divided by h. Now what happens? That is equal to limit h tends to 0 minus f of h means modulus h minus f of 0 means modulus 0 divided by h. So that is equal to limit h tends to 0 minus mod h. What is mod h? Here h is negative because h is approaching 0 taking values less than 0. Therefore we have negative h here by the definition of a absolute value function, then divided by h. So that is equal to negative 1. And when we consider the right hand limit, that is right hand derivative here, that is limit h tends to 0 plus f of 0 plus h minus f of 0 divided by h, that is equal to limit h tends to 0 plus modulus h by h. You know, f of 0 is nothing but f of 0 is nothing but mod 0 is 0 only. So we have like this, and here you can see that h is becoming positive. H tends to 0 plus means h is positive. Therefore, what about a modulus h? Then modulus h will be h only. So limit h by h as h tends to 0 plus, that is equal to 1. So we can see that we got the left hand derivative as negative 1 and the right hand derivative as 1. So we don't have a common value for the limits here. So LHL not equal to RHL here. Therefore we cannot speak of, that is f dot 0 limit f of 0 plus h minus f of 0 divided by h as h tends to 0 doesn't exist, means f given by fx is equal to modulus x is not differentiable at x equal to 0, not differentiable at x equal to 0. So here you can see why it is not differentiable in a visualization way. That is, actually, you know, the geometrical meaning of the derivative is nothing but, suppose this is the curve, say y is equal to f of x, and this is the x-axis, y-axis origin, and you can see that let this point be, say, c, x equal to c. Then if we consider the tangent at this curve at the point, this point is c f c, this point is c f c, that is x coordinate is c and y coordinate is f of c only, because function is y is equal to fx. Then if we draw the tangent, then the slope of this tangent will be the derivative f dash c that we know. And we can now see that when the curve is having a sharp bending like this, if the curve is having a sharp bending like this, then at that point we cannot have a tangent. That's a problem. So here, you know, modulus function, the graph is somewhat like this. That is, the graph of modulus function is having a sharp bending like this. When a sharp bending is here, at that point we cannot speak of tangent. That we are going to visualize. We can see using a curve which is having a sharp bend. Then we will see that wherever the curve is having sharp bend like this, then we cannot find the derivative at that point. Let us have the visualization and come back.
I told you, whenever there is a sharp bending on the curve like this, the function will not be differentiable at that point. Now we are taking the left hand derivative, that is, we are taking the tangents from left hand side of a. Then you see the blue colored tangents we are getting, and when we take the tangents from right hand side, that is the red colored line, you can see that when we approach a, we are in dilemma, which is the tangent to be taken. So there is no tangent. No tangent means no slope. And the slope is what is called the tangent slope is what is called the derivative. So no derivative. So the function is not differentiable at a capital A. So whenever a function is having a sharp bending like this, at that point function is not differentiable. Let's consider the function, modulus function, that is absolute value function, and now we are taking the tangent at any point on the left hand side wing, and we are considering the tangent at any point on the right hand side wing. But at the origin, what is happening? We are in dilemma to take which is tangent we have to take. So there is no unique tangent means no tangent. No tangent means there is no derivative. Therefore, the modulus function is not differentiable at x equal to 0.
Okay, so what we could prove is that whenever a function is differentiable, then it has to be continuous automatically. It has to be continuous. But if a function is continuous, we cannot say whether it is differentiable or not. It may be differentiable, it may be or may not be. That is according to the situation or according to the given function. That is, when a function is differentiable, it has to be continuous, no doubt. But if a function is continuous, then sometimes, in some cases, it can be differentiable, and in some other cases, it cannot be differentiable. That is, continuity doesn't imply differentiability. How to recollect this thing?
Do you know English alphabet? Yes, I know up to D. Yes, he says he knows up to D. That means certainly he knows C. Therefore, when a function is differentiable, it is continuous. Knows up to D means C is known. Therefore, function is given to be differentiable means it is continuous. Do you know English alphabet? A, B, C, C, C. Now what will happen? Sometimes he may continue. He can say D, E, F, G, H, etc. Or sometimes he may say, sorry, I don't know the remaining letters. That means if a function is continuous, then it may be differentiable sometimes or it may not be differentiable. That will depend upon the case.